His background is in experimental quantum optics, quantum signal detection, and high-dimensional quantum information. And he has over 7 years of postdoctoral experience in experimental quantum photonics engineering. And so he'll tell us a little bit about the quantum weirdness of the quantum world this evening. So I'm delighted to welcome you, Untitled, and over to you.
Thank you very much, Sarah. Hello, everyone. It's nice to have you all here today and to share together on this topic of quantum key distribution, which is one of the ways in which we exploit the weirdness of the quantum world. All right, so let's get started on that. So, of course, this is just one aspect of quantum technologies. That is a group of technologies that harness the weirdness of the quantum world. So other aspects include computing, where you have specifically search algorithms that perform better than is possible with ordinary computers. And also you have imaging, you have quantum metrology, which is ways to measure with precision that is impossible to achieve without quantum mechanics. And then you also have simulating quantum systems, which is done most efficiently by applying the laws of quantum mechanics as well. So we're going to focus today on this aspect, secure communication. Good, so in order to do that, let's introduce the concept of cryptography. So what is cryptography? Well, cryptography refers to ways of encoding information, okay? Sensitive information. So you have a message that you'd like to send to another party.
Sorry to interrupt. We don't have your slides yet.
Oh, you don't have my slides. Sorry about that. Sorry, I forgot to share my slides. Just a second. And there you go. Okay, thanks very much for that, Sarah.
Perfect.
So this was the first slide, and this is the second slide. And I'm now on this one. So cryptography. All right. So as I said, cryptography refers to ways of sharing sensitive encoding and sharing sensitive information. So the idea is you have a message that you want only one other party to be able to decode, and you kind of transform that message into a way, into a form whereby no one else can read it except the right recipient of the message. So we're going to introduce some of the earliest known methods of quantum cryptography, and then we're going to also show some provably secure methods. And then we'll see what loopholes exist in these classical methods, and eventually we'll see how quantum physics comes to the rescue in that regard. Okay, great. So the first one we're going to consider is the Caesar Cipher. So this is one of the earliest known methods of cryptography, and it's really straightforward. So basically what you do is, for example, if you'd like to write a message using the alphabet A to Z, so what you basically do is shift the alphabet by a fixed amount. So in this case, you shift it by 3 so that D comes to the place or to the position of A, and then you do it in a cyclic way so that you have ABC at the end. Then any message you write, so for example, if you want to send a message that looks like this: Bob, meet me at 8, Alice. Then what you would have, by applying that encoding scheme, you would have something that looks more like this, which I can't even read because it's just jumbled up text, isn't it? So as you see there, in order for someone to kind of decipher that message, then they need to know what system you've used to encode it. So if they know that you shifted the alphabet by three places, then by shifting it back 3 places, they can recover the message. So this is another one, variable shift. So this is a little bit more secure in the sense that you basically, instead of shifting the entire alphabet by just a fixed amount, so you have everything just shifting by a fixed amount, you basically scramble up the alphabet. So you shift by varying amounts, but you still have this uniqueness. There's still a one-to-one correspondence between the plain text and the cipher, okay? So that's a little bit more secure, but there's an even more secure method, which is what we're going to look at next, and that's a random shift. So basically this one, instead of having one-to-one correspondence, you actually have a truly sort of random amount of shift for each individual letter in your message. So in this case, for example, B, the shift is 17 here, and it's 13 here, and it's 2 here. So the ciphertext is a lot more secure in this case. In fact, this scheme is provably secure, and it's the core principle behind the most secure form of cryptography, most popular form these days, and that's the one-time pad. So let's have a look at what that looks like then. One-time pad, how does it work? So for example, if we want to encode a message like this, 8 p.m., and so of course we know that the popular form of encoding information in our age is in binary format, because that's the language that computers understand, isn't it? So in zeros and ones. So if we convert this into the binary format using the ASCII code, so what we have, 8, the plain text we have in zeros and ones is given as these. So how do we apply the one-time pad? Well, the one-time pad is basically goes in this way. So you have a key, which is another string of zeros and ones of the same length as the plain text message that you want to encode. And what you then do is apply an operation called an XOR. So basically what that XOR is an operation that outputs 1 when the 2 inputs are different, right? So for example, with 0, they're the same, so it's 0. 0 and 1, well, they're different, so you have 1. 1 and 0, they're different, you have 1, and so on and so forth, and so on and so forth, right? And you continue with that, and then you come up with this key or this ciphertext, which you can then send across. So what does this look like in sort of normal sort of characters that we use? Well, it looks something like this: J, fast forward or whatever this is, and then a space bar, a space, and this basically doesn't mean anything, does it? So that's an example of the one-time pad encryption. And of course, if you want to decrypt this, all you have to do is apply that in reverse. So you basically apply the one-time pad once more, and then you arrive at the message. So if we start with this, and we get the ciphertext, which is the ASCII code for these characters we have here, and then we use the same key and apply the one-time pad, which is the XOR operation again. What do we get? Well, we get that, which was the string of zeros and ones that we had before, and that is just 8 p.m., which is the message that we wanted to encode. All right, so you notice here we have, just as we had in the other case, we had the shift. Here we have a key, and this key is the secret, is the very important aspect of performing this encoding or this encryption. Now, there is a problem here. So anyone who gets the key or has an ability to read or view the key can decode the message, okay? So if for example, Alice is wanting to send a message to Bob, and someone manages in one way or the other to get to know what the key is, then such a person might do so without Bob ever knowing or Alice ever knowing. And that creates a problem. So that's a loophole in the classical methods for encrypting information for cryptography, okay? So how do we solve this problem? Well, there is let's go, fantasize a little bit about a possible solution. And this is using what we're calling here magic boxes. So how do these boxes work? Well, now just imagine you have these magic, wonderful boxes. So you have two of them, they come in pairs, and they have this amazing sort of connection between themselves, whereby if you put a coin in one of the boxes, and if you open one of the boxes, the other box shakes in such a way that if there's a coin in it, the coin will flip with probability of 50%. So that's what we have here. Whenever one box is opened, the other one shakes so that the coin is flipped with a probability of a half. Okay, so how can we use such a box to distribute keys in a way that if someone listens to the key, we will be able to detect the presence of such an eavesdropper? Well, now imagine Alice trying to do this. So Alice puts the coins in the boxes, puts a coin in one of the boxes, and she chooses at random which of the boxes she will put a coin in. Now, so for each bit she wants to send, she does that. So each bit is represented by a pair of boxes, and she puts a coin in one of them randomly. But she knows which box she's put it in. So she knows if it's red or yellow. So red for the first one, yellow for the second one, and so on and so forth, right? Now, what happens if she places in each of the boxes, she places either heads or tails? Again, she makes a note of, yellow heads for the first one, and so on and so forth. So then she takes this pair of boxes and sends them to Bob. So now when Bob gets the boxes, Bob then decides to check one of the boxes first, of course. Of course, remember that when Bob checks a box, the other one shakes, right? So if Bob checks the right box that has the coin in, then Bob sees exactly the coin that is placed by Alice, and he sees whether it's it's heads or tails, and it's correct. It matches what Alice actually put there. But if Bob chooses the wrong box, then his action of checking the first box might flip the coin in the second box. So by the time he sees the actual coin, where the coin is, it might have been flipped with a probability of a half. So when they make the call between each other and try to compare which sort of boxes have the coins and what the actual value of the coin is, whether it's heads or tails, then what happens is, in the case where the first case where Alice and Bob choose the same color boxes, that is when Bob chooses to look at the one with the coin, then their bits agree. So if Alice had put a heads, then Bob sees a heads, and so on and so forth. But in the case where Alice or Bob looks at the wrong box, where there's no coin, but you kind of make the other box shake, then what happens? Well, because of the probability of flipping the coin being a half, Bob will agree, Bob's bits will agree with Alice's prepared state half of the time, okay? Now, in those cases, you basically just throw that information away because there's errors in it. However, what if someone tries to listen or tries to check the boxes before Bob actually gets to check them? Well, what happens is that if the eavesdropper has a look at the boxes, when the eavesdropper opens the wrong box, of course, the coin is flipped with probability of a half. And the effect of that is that there will be errors. So by the time Alice and Bob compare their bits, well, you'll find errors. In the case where there shouldn't be any errors, you'll find some errors. So that way you'll know that someone has listened, and then you discard the key and you won't use it, of course. So that's basically, that would be a wonderful thing to have. So wouldn't it be nice if something like that could happen in reality? Wouldn't it be nice to have, a way to kind of implement that? If that was possible, then you would actually have an unbreakable scheme for information encryption. Well, it turns out that it is possible thanks to quantum physics. So to show you why that's the case, well, let's just introduce a few concepts in quantum physics. And the first is the key ingredient, which I'm going to introduce. So to introduce that, I'd like to talk about states, okay? In our everyday intuition, we're used to states. So for example, take a switch. A switch can be in two states, a switch like this, on-off switch. So it could be on or it could be off, right? Well, it turns out that in quantum physics, the switch can be on or off, but also it can be in a state that is in what's called a superposition of both on and off. And this state is really interesting because it basically tells you that the switch is basically undecided. It hasn't decided whether it's on or off. It's somewhere sort of, it's both in parallel at the same time in some really weird way. And that's the magic, that's the X factor that you can apply. So it's really similar to how the magic boxes work. And in fact, you can even have a situation where you have not just one switch, but you have two. And the two switches can be correlated. So if one is on, the other will be off. And if one is off, the other will be on. A little bit like those boxes where if one is empty, the other has the coin. And if one has the coin, then the other is empty and so on. And if you measure one, if you open one, the other one shakes. So it has an effect on the other one. So something similar to that. And it turns out that in nature, in physics, it actually exists. This actually exists, and it's something you can measure and demonstrate in the laboratory. So in this case, if it's two or more, components in the superposition, you have what's called entanglement. Anyway, so the particles that have these characteristics are called quantum particles, and a very good example is the photon. So we know light is made up of, fundamentally made up of the indivisible particles, which are called photons. So it has this particle or grain-like characteristics. Now, each photon has different properties. One of the properties could be, for example, the color of the photon, which is the energy of the photon. But you also have something called polarization. Now, we know light is also electromagnetic waves, right? Now, the direction of oscillation of the electromagnetic wave or the oscillation of the electric field is called the polarization. And that's something you've looked at, you've already interacted with a little bit, I'm sure, in this school. So I'll just illustrate it using this. So for example, you could have horizontal polarization if the oscillation is in the horizontal direction, and you can have vertical polarization if it's oscillating in the vertical direction. Of course, you can also have superpositions of horizontal and vertical. And in that case, you'll have that oscillation defined in the, for example, diagonal direction or the anti-diagonal direction. And in physics, we call these two states orthogonal. That is, there is no component of one in the direction of the other. And these pairs are orthogonal pairs, okay? And of course, you've also looked at polarizers. So polarizers can enable you to create polarized light. So a light that passes through a polarizer on the other side, the light has a defined polarization. And you can use a polarizer as well as a means to measure polarization, right? Now, so in the case of polarization, the quantum superposition is just saying that the photon is in a state where it is in H, horizontal polarization, and vertical polarization kind of in parallel, and it hasn't made its mind up until you ask it, what's your polarization? And then it tells you, are you vertical or horizontal? Then it kind of collapses into one of the possibilities. So such a state is something that is really useful in quantum technologies, especially quantum-enabled sort of cryptography. So just to give us a little bit of intuition on this, so if the state coming in is horizontally polarized, and we use something we call a polarizing beam splitter, which basically sends a state, reflects the photon depending on the polarization. So if the polarization is vertical, it reflects it. If it's horizontal, it just transmits it. So this way we can measure. So we pass this through, it pops out here if it's horizontal. And if we pass this through, it pops out there. So what happens if we send a diagonally polarized photon into this setup? What happens? Will it pop out here or will it pop out there? Does anyone want to maybe tell us? Well, it will pop out. Oh, is someone telling us? Let's have a look. Both. Nice. Thanks. Thank you very much, Thomas. Well, it will pop out either here or there. So in a sense, well, it will in parallel go this way and that way until the detector checks, are you here or are you there? And when it clicks, once the detector clicks, then it would have made a decision, well, okay, I'm here because you got me, all right? And then you will either have it popping out here or there with 50-50 chance, 50-50 probability, okay? Okay, so similar for the anti-diagonal polarization. Okay, so I'll just skip this. So the probabilities are kind of highlighted here in this table. You've got for different bases of your measurement. You can measure, for example, you can ask the question, are you H or V? If you ask that question, if it's H, then you have probability of 1 of popping out as H. If it's and the probability of 0 popping out as V. If it's V, it's reversed. And if it's diagonal, you have 50-50 probability of popping out as H or V. And you have something similar with asking the question, are you anti-diagonal or diagonal? And in this case, the 50-50 probabilities will be when you have H and V, and DNA will give you 100% probability to answer D and 0% probability, and so on. Okay, so let us see how we can apply this then. How can we use this for cryptography? Well, instead of using the magic boxes, if Alice prepares what's called qubits or quantum bits at random. So you remember in the case of the magic boxes, we had read, Alice put her coins in the yellow or red at random, right? In this case, Alice prepares at random in H or V. So she prepares each photon in either H or V or in A or D. And in each case, she notes the bases and the bits. So the bit will be 0 for H and 1 for V, or for A and D, depending on which basis she uses. Then she sends that to Bob, and Bob then measures these bits. And in the case of, if Bob chooses to decide to ask the question, are you H or V? And he gets 0, or 1, he makes a note of both the measurement he did and the results he got. Now, the next phase will be Alice and Bob make a call and check with each other. So for the first one, which basis was it? They see if the basis agreed, and then they see what a value of the bits were. Now, in the first case, if Alice and Bob choose the same basis, then if nobody listened, all their bits will agree, right? But in the second case, if Alice and Bob choose different bases, then only half of the time will their bits agree, okay? So very similar to what happened with the magic boxes that we talked about earlier. So what if someone listens? What if someone listens to the message? Well, it will have the same effect. The effect will be that Alice and Bob's sort of keys, when they're supposed to be completely in agreement, there'll be errors in there. And so that way you solve the key distribution problem. And even if someone at gunpoint asks for the key, it's useless, because anyway, you're gonna know by doing the measurements, you'll know that this key has been compromised. So that is how quantum mechanics or quantum physics comes to the rescue when it comes to the key distribution problem. Okay, so there we go. Now, just to conclude, I'd like to demonstrate very quickly an aspect of quantum physics. So the key ingredient, which is superposition, all right? And to do that, I'm going to stop sharing for a moment. Oh, actually, before I do that, let me just walk you through what the experiment does. So the experiment that I'm going to demonstrate. So first of all, this experiment has, as you can see here, a laser. The laser is the source of the photons. And the photons, as we said, are particles at the fundamental level. They behave like particles. So let's consider the case of a single photon. So when a single photon goes through this setup, it comes out of the laser, goes through a lens, and bounces off a 50-50 beam splitter, which is, you can think of it as a half-silvered mirror, which reflects a photon or transmits it with 50-50 probability. So the first case, if it was an everyday object, what would happen would be the photon comes, bounces off, and goes to the screen. The other option would be photon comes this way, goes through, bounces off the mirror, and goes to the screen. Now, in the case of a quantum particle, which is really what the photon does, well, the photon comes this way, and then it gets here, goes in a superposition of both, and gets back to the screen. So you see, instead of choosing one here or the other, it splits into a superposition of both parts, comes back, and then it reflects off the mirror of the beam splitter. Now, the effect of that superposition is that on the screen here, you see, instead of having a blob of light, you see an interference pattern. And that's something that I'm going to demonstrate very briefly now. So I'll just share my other camera. Just a second. Okay, there we go. Okay, so that's the screen. And I'm going to show you just a second. So this is the actual experimental setup. Okay, here we go. So here's the experimental setup. And what we have is, as I said before, the laser. So this is the laser coming with the light coming out. And this is the lens, and you have the beam splitter here. So there are two possibilities. The light comes this way, bounces off the mirror, and goes off to the screen, or it comes straight and comes back and bounces off right? So here we've kind of tried to simulate what happens in the case of a classical or an everyday object. So in that case, we've put a polarizer in each of the arms, and each of the polarizers are oriented in orthogonal in perpendicular directions. So what happens is, because we've put the polarizers there, we've made it possible to distinguish where the photon went through. And that then means that the photon has been forced to make the decision. So we've made it possible to see which path the photon went through. Now, I would like to show you what what it looks like on the screen when that's the case. So we see here on the screen, we just see a blob. That's what you expect for normal everyday objects. So I'm going to remove the polarizers now, and you see that. Now that's the effect of the quantum interference. That's a very weird thing, which happens at the level of a single photon. So you only see this pattern because the photons, instead of going one direction at a time, they actually, each photon goes in both directions at a time and comes back and interferes with itself, and it creates this pattern. So, well, I hope that has interested you a little bit. And with that, I'll just conclude with my final slides. Okay, back to that. So I hope your interest in quantum physics is a little bit more now, and I hope I've been able to convince you that quantum physics makes otherwise impossible things possible, and it's in this case the solution to the distribution problem in cryptography. Thank you very much for listening, and please, your questions are welcome.